So today we're going to start from the second part of the video, which is about the state function. The internal energy of a system depends on many things, which are the chemical identity, sample size, temperature, pressure, physical state, which is the gas, liquid, or solid, and many more. And the internal energy does not depend on one thing, which is the system's past history. It means that it doesn't matter what the system's temperature or physical state was an hour ago, and it doesn't matter how much the chemicals were obtained. All that matters is the present condition of the system. So, internal energy is said to be state function. We're linking this topic to the previous topic in the previous video, and one of this topic is related to the thermodynamics overall topics. So, one whose value depends only on the present state of the system is the state function. Pressure, volume, and temperature are other examples of state functions, and to be noted here is that work and heat are not state functions. Which one of the following is a state function? The speed of the car on the highway or the distance of the route from Sialkot to Lahore? This is a quick IQ test to tell me in the comment section below. The next thing we're going to talk about is a system's work. A system can do two kinds of work. The first is the expansion work and the second one is non-expansion work. In chemistry, we mostly deal with the expansion work, which is related to the change in the volume. So the first type, expansion work, is the work arising from a change in the volume of a system. A gas expanding in a cylinder fitted with a piston pushes out against the atmosphere, and thus it is known as expansion work. And the non-expansion work is the second type of the work done by the system on the surroundings, and it is a work that does not involve a change in volume of the system. A chemical change in a battery can do non-expansion work by causing an electrical current to flow, and even our bodies do not non-expansion work when we move about. So here we know about the non-expansion and the expansion work. Expansion work means the one in which volume is expanding, and non-expansion work means no volume change. So here we're going to talk about the expansion work. Just as energy comes in many different forms, work is also of different forms. And in physics, work, which is denoted by W, is defined as the force that produces the movement of an object multiplied by the distance it has moved. So here we're going to talk about the expansion work. W is equal to F into D. So mostly when you run upstairs, for instance, your leg muscles provide a force sufficient to overcome the gravity which is pulling you downwards towards the earth, and that force lifts you higher. And mostly when you swim, you provide a force sufficient to push water out the way and pull yourself forward. So this is the type of work you do. So most common type of work encountered in chemical systems is expansion work. It is also known as the pressure volume work or the PV work. In a reaction of propane with oxygen, we see that the 6 moles of gas along with oxygen form 7 moles of the gas as resultant product. So that means that there is a volume change in this reaction. So there is expansion work. It was the simplest example, and for expansion work, the simplest example is the work done by a system consisting of a gas in a cylinder. The external pressure acting on the outer surface of the piston provides the force opposing the expansion. So we can assume that initially the external pressure is constant, and when the piston is pressed on by the atmosphere, there is a constant pressure from outside. So we need to find how the work done occurs when the system expands through a volume of delta V, and delta V is related to the external pressure, which is PEX. So the work done in a system can do its expansion against the constant pressure, and it is calculated, and this calculation is known as work calculation. Therefore, the work done by the expanding gas will be P external into delta V. We will prove it through the formula. P is equal to F over A, as we know pressure is equal to the force applied on certain area. Now work done is equal to the force multiplied by the distance covered. So now the work done will be equal to the pressure external multiplied by the area into D, because F is equal to P external into A. So F is equal to P external into A, so that makes that force quantity changed into P external into A. So the work done will be P external A into D. Now the volume is equal to the area multiplied by the height. A is multiplied by D, which is equal to the delta V, as we can see in the figure. So we can prove it mathematically and clearly see in the picture given. I'm hoping that I can explain all the basic concepts in these two videos so that I can clear you other concepts about enthalpy, entropy, and Gibbs free energy, which are the heart of the thermodynamics. So work is equal to the P external A into D, and here goes the derivation, which gives us work is equal to minus P external into delta V, which is the expression which is applied to all the systems. A gas is easiest to visualize in this case, but the expression also applies to an expanding liquid or solid. However, the equation applies only when the external pressure is constant, as I told you before, during the expansion. So the minus sign, the sign convention here is negative. This minus sign in equation tells us that the internal energy of the system decreases because some energy is lost as work when the system expands, and the factor PEX tells us that more work has to be done by the system when the external pressure, which is responsible for the opposition force, is very high. The factor delta V tells us that for a given external pressure, more work is done when the system expands by a large amount. So in SI units, the external pressure is expressed in pascals, where 1 pascal is equal to 1 kilogram meter per second square. And the change in volume is expressed in cubic meters, which is M3. The SI units of work can be found from the product of 1 pascal and 1 meter cube. Therefore, 1 pascal meter cube is equal to 1 kilogram meter per second square. And here are some conversions. It is equal to 1 kilogram meter square per second square, and which is equal to 1 joule. So when a reaction takes place with a contraction in volume rather than an expansion, the delta V term has a negative sign and the work has a positive sign. This is again consistent with adopting the point of view of the system, because the system has now gained work energy, which means that E final is greater than the E initial. For example, in industrial synthesis of ammonia by reaction of hydrogen with nitrogen, 4 moles of gaseous reactants yield only 2 moles of gaseous products. So the volume of the system contracts and work is gained by the system, which is clearly a contraction. Here the sign convention will be delta V is equal to minus, which is negative,